Previously, in the RH Saga, we talked about the Millennium Problems related to L functions, but we postponed the BSD Conjecture. In the early 60s, Brian Birch and Peter Swinnerton-Dyer were exploring solutions to elliptic curve equations, like our old friend y squared plus xy plus y equals x cubed minus x. They used the EDSEC2 computer machine at University of Cambridge, and the pattern they found was an unbelievable connection between solutions in finite number systems and solutions in infinite number systems. Proving this connection has become one of the main unsolved problems in all of number theory, and maybe all of mathematics. One version of this BSD conjecture even implies the generalized Riemann hypothesis for the L function of an elliptic curve. But let's place this problem in the wider context of the RH Saga. We seek to understand L functions. Traditionally, L functions are constructed from primal objects, by which I mean motives, Galois representations, flat schemes, and automorphic representations. But many of the deepest problems around L functions apparently cannot be solved within these existing paradigms of primal objects. Maybe because a primal object assembles an L function from information collected separately from each prime. The dream is to find this new world called F1 geometry, which would be a new paradigm for how to construct L functions, in which some unsolved problems could be approached from a completely new perspective. We have chosen to focus on the most immortal unsolved problems, like the Millennium Problems, RH, BSD, Hodge, and also the Langlands program. Of course, there are many smaller and more approachable problems which could and should be used as test cases for any proposed F1 geometry. As a foundation for approaching F1, it is absolutely necessary to have a solid understanding of what's already known about L functions. And this understanding is what we have been sketching or beginning to build. We introduced a few examples of L functions coming from objects we called P, K, A, and E. These examples are really just selected representatives of the four most basic classes of L functions. The Riemann zeta function itself, a unique example. The Dedekind zeta functions coming from number fields. The Dirichlet L functions from Dirichlet characters, and L functions from elliptic curves. We talked about axioms for L functions, and we ever so briefly touched upon the idea of representations. An L function can be represented as a Dirichlet series, but also as an Euler product, or as an integral of some other function. Then we studied machines, by which I mean operations of different types. This led to the idea of the fundamental objects L, the space of all L functions, which should be a lambda ring and a Hilbert space, and also the dual space L star, which contains the prime numbers, the prime powers, and in general all additive invariants of L functions. But now, let's dive into the BSD conjecture, where, among other things, we shall encounter one of these additive invariants, namely the analytic rank. A Diophantine equation is an equation where we look for solutions in rational numbers or integers. Such equations can be either polynomial or non-polynomial. For example, x cubed plus y cubed equals z cubed is a polynomial equation. This is one case, the simplest case, of the equation appearing in Fermat's last theorem. A non-polynomial example would be 1 plus 2 to the x plus 2 to the 2x plus 1 equals y squared. This is an IMO problem from the International Mathematical Olympiad in 2006. For both of these, the original problem statement is to describe all integer solutions. However, the Fermat equation has a special property. It is homogeneous, meaning all terms have the same degree. In this case, 3. When this happens, we can rewrite the equation by choosing a variable, so I choose z, and dividing everything by z to the power 3. This gives us x over z to the power 3 plus y over z to the power 3 equals 1. And if we call these brackets, say, lowercase x and lowercase y, we have the new equation x cubed plus y cubed equals 1. There are 2 points I want to make here. First, this new equation has only 2 variables instead of 3. Second, every hypothetical integer solution to the original would give a rational solution to this new equation. There is an exception here if z is 0. Often with Diophantine equations, we focus on the rational solutions rather than the integer ones. This sometimes allows us to reduce the number of variables, as we did here, and in any case, the rational solutions will always include the integer solutions as a subset. Some terminology. A solution in rational numbers is called a rational point. A solution in integers is called an integral point. For example, we could say that 423 is an integral point for this IMO equation. And of course, the Fermat equation does not have any rational or integral points. Now, let's zoom in on the polynomial equations. The goal for any equation is to find all rational points, or at least to say how many there are. We can classify equations by the number of variables, say 1 variable, 2 variables, and 3 or more variables. The 1 variable case is very easy. Just take some equation, say this one. If x is a rational point, we can write it as a over b. Here a must be a divisor of 2, the constant term, and b must be a divisor of 3, the leading term. Therefore, the only possible solutions are 1 over 1, 1 over 3, 2 over 1, and 2 over 3, and each one could have a plus or a minus sign. So this is a finite list of candidates. We can check them all by just plugging into the equation. In this case, we find that x equals minus 2 and x equals 1/3 is the complete list of rational points. With 3 or more variables, the math becomes very hard. Here, you may encounter things like the unsolved Bombieri-Lang conjecture, or ideas like the Brouwer-Manin obstruction, developed by Yuri Manin. This concept of Manin is related to the idea that an equation may have solutions mod p for all prime numbers p, but still no solutions in integers or rational numbers. In two variables, we classify equations by an invariant called the genus. These equations are called curves because if you plot the real solutions, the graph is a one-dimensional curve in the two-dimensional plane. If you could plot all the complex solutions, that would be a two-dimensional surface in four-dimensional space. Hard to visualize, but topologically, it has to look like a sphere or a donut or a double donut or some similar higher donut. The number of handles here is defined to be the genus of the equation. As a rule of thumb, you can think that genus 0 corresponds to polynomials of degree 1 or 2, and genus 1 to polynomials of degree 3. Genus 2 and above means roughly equations of degree 4 and above. So, an equation in two variables may have genus 0, genus 1, or genus higher than 1. Genus 0 is easy. Here, if you can find a single rational point, let's call it the base point, then there is an infinite number of rational points. But you can write all of them down with one simple formula. One example. The Pythagorean equation is x squared plus y squared equals z squared. Rewriting as before, we get x squared plus y squared equals 1. That's a circle. And all rational points are given by the formula x equals 1 minus t squared over 1 plus t squared, y equals 2t over 1 plus t squared, where t is either a rational number or t goes to infinity. Geometrically, the idea is that from the base point, you draw a line with rational slope t, and that constructs every other point xy. You need the case t goes to infinity because that corresponds to the base point itself. At the other end, genus 2 and higher is hard. Falting's theorem says that the number of solutions is finite. There is no general method for finding all solutions, like we had in the one variable case, but many very, very interesting partial methods. For example, the method of Chaboty. Anyway, at the heart of all these Diophantine equations, we find the curves of genus 1. And such a curve, together with the choice of base point, is called an elliptic curve. Not too easy, not impossibly hard, they are in the Goldilocks zone where you can get started with exploration quite easily, but as you dive further in, they unfold and reveal incredibly deep structures. The equation for an elliptic curve is often written as y squared equals x cubed plus ax plus b for some constants a and b. But that is a simplified version of the general form, also called the minimal form, which is y squared plus a1xy plus a3y equals x cubed plus a2x squared plus a4x plus a6. Here, a1, a2, a3, a4, and a6 are constants called the Weierstrass coefficients. For our elliptic curves, these will always be integers. In fact, these two are 0 or 1, and this one is minus 1, 0 or 1. Very importantly, these Weierstrass coefficients are not the same as the Dirichlet coefficients a1, a2, a3, etc. appearing in the L function. Pick an elliptic curve in the LMFDB. Now, you can choose whether to display the simplified form or the minimal form of the equation. You can also choose here the homogeneous form with an extra variable z. Then all the terms have the same degree, namely 3. Now, let's take our favorite elliptic curve, 14.A5, and see if we can find some rational points. Before, we did this mod p. Now, very different story. We look for integers or rational numbers, x and y. Factoring both sides might still be helpful. Y times y plus x plus 1 equals x times x minus 1 times x plus 1. Some solutions could come from both sides being 0. Those we can spot from the factorization. For example, if x is 1, the right-hand side is 0. In the left-hand side, I can then choose y to be 0, or I can choose y to be minus 2 to make the bracket 0. Working out the other cases, I find 5 solutions already. These 5. But there could be more solutions. I could try any x, like x equals 6, and then solve the resulting quadratic equation for y to see if I could get a rational number there as well. Using trial and error like this, or computer search, you can try lots of different x and y values, but you would not find any more rational solutions. Having tried that for a while, you would start to think that maybe you have found all rational points already, this finite set in the table. But could you know for sure? Perhaps there are more solutions, maybe infinitely many solutions, and you just didn't search far enough. Another example. Take y squared plus y equals x cubed minus x. This is 37.A1 in the database. Again, we can guess some rational points, like y equals 0, x equals 1. And you can guess a few more. But now, it's very different. You can try some x values and solve for y. With hindsight, I now try x equals 6. Right-hand side is then 6 cubed minus 6, that's 210. Can you get to 210 with y squared plus y? Well, 196 plus 14, that is 210. And this is 14 squared. So y equals 14 works with x equals 6. We can keep searching. X and y don't have to be integers. They could be other rational numbers. And with some patience, you could probably find x equals 1/4 and y equals minus 5/8. Think about how you could have guessed that 4 and 8 are plausible denominators for x and y. If we did a computer search, it would seem like we keep finding more and more and more points, seemingly an infinite list. But again, we cannot know. Maybe there are lots of solutions, but at some point down the line, it stops, and we've found them all. A finite set. We could do other examples, right? Take any of the curves in the LMFDB list. I'll just pick 2 more for future reference. Y squared equals x cubed minus 108. Can you find any solutions to this one? Or look at y squared plus y equals x cubed plus x squared plus 13x plus 42. In each case, we want to find all rational points. But a more high-level question, perhaps the fundamental question, is the solution set finite or is it infinite. Almost everything we did in the overview was about this fundamental question. Here it was a finite, here it was infinite, here it was finite, and even the Bombieri-Lang conjecture is, in a more abstract sense, about the finiteness or infiniteness of the rational points. So how do we know? How do we know for a given elliptic curve? And here, the answer is sensational. I think it is beyond anything you could possibly dream of. The answer is that the L function knows. The L function of the elliptic curve knows whether the solution set is finite or infinite. Before revealing how it could possibly know, I have to show some examples. For the first example, 14.A5, the solution set is indeed finite, and the L function graph for real input values looks like this. The second example, 37.A1, the solution set is indeed infinite. The L function looks like this. If you tried the 108 equation, you may suspect already that there are no solutions. And that is indeed the case. So definitely finite. The L function looks like this. The last one, 91.B3, if you searched with a computer, you would find lots and lots of solutions. And the L function looks like this. Recall that if we multiplied with those gamma factors, each of these functions had a symmetry line at s equals 1. The value at s equals 1 is called the central value. Here it is positive, here 0, here positive, and here 0. And now we have arrived at the simplest version of the BSD conjecture. For an elliptic curve E, having infinitely many rational points is equivalent to the central value being equal to 0. So, is this statement true? We don't know. It is supported by millions and millions of computed examples similar to the 4 we just saw. Also, the implication has been proven in the forward direction. That is some very deep work by Kolyvagin and others. So, if there are infinitely many solutions, then for sure the central value is 0. But the other direction, no one knows how to prove that. This was the simplest version. The BSD conjecture can be made much more precise. The standard version is that for any elliptic curve E, the algebraic rank is equal to the analytic rank. In the next episode, this BSD story continues, and the goal then will be to say precisely what is the algebraic rank and what is the analytic rank. And we will also be looking for some possible further clues for F1 geometry.